Okay. So, today what I am going to talk about is this Perez-Horodecki criteria for separability of any two mode Gaussian states. Okay. So, this is what I am going to talk about. There are two papers consecutively. So, the thing which I will follow here is this paper by R. Simon. This is PRL 84, then page number 2726 2000. There is another paper which, if time permits, I will also discuss little bit. This is by Lo-Ming Duan et al. PRL 84 volume, page 2722 2000. Just this is the one which is just before this one. Okay. They appeared in the same volume, same issue actually. Okay. Good. So, let me first so, as I said, I will just follow this one. If time permits, I will also tell little bit about this. Okay. Not today, later. Okay. So, what is the issue here? So, we know that if I take a state rho A B, a bipartite state, which is acting on the composite Hilbert space H A B, which is H A tensor product H B. Okay. So, it does not matter whether this is finite dimensional or infinite dimensional, then this state is separable. So, that means it does not have any entanglement if it can be created using classical communication and local operation. So, in the sense that rho A B can be represented as, so this can have infinite sum also. In that case, one should talk about the convergence of this series. So, P j sum j for A, I mean you can take rho also, but that does not matter. I mean this is a different rho. Okay. B. So, these P j's are probabilities, sum over j P j is equal to 1, and this rho j's rho j k. So, this is density matrix of the kth subsystem, where k is equal to A and B here. Okay. So, this is the standard definition of separability, right. And the necessary condition which was given by Perez, necessary condition for separability is that if I perform what is known as partial transposition. So, then this will go to rho A B T B, you can also take T A. So, which is basically you apply this map, transpose map on the B part of rho A B. Okay. So, the necessary condition tells you that if this is separable, then if I apply this partial transposition, it will take me into rho J A tensor product, rho J B its transpose, and because this is a density matrix, this is also a density matrix, which let me call it as rho prime B J. So, therefore, this is also a separable state. So, Perez-Horodecki criteria tells me that under partial transposition a separable state remains separable. Okay. This is the necessary condition. Okay. Now, we know that when dimension of H A is equal to 2 is equal to dimension of H B, or dimension of H A is equal to 2, dimension of H B is equal to 3, or this dimension of H A is equal to 3, dimension of H B is equal to 2. In all these cases, this necessary condition is also sufficient. So, rho A B is separable. This is equivalent to this condition, that if I take the partial transposition, it does not matter whether I take on B side or A side, this should be greater than or equal to 0, because separable state is, it is a state. So, therefore, under partial transposition this is the case. In all other dimension, we know examples where this is not sufficient. So, this is necessary and sufficient for this dimension, but otherwise it is not in other dimension. Okay. So, what we are going to show is that if I take a 2 mode Gaussian state, I mean special kind of 2 mode state, then this is again necessary and sufficient. Okay. So, for 2 mode Gaussian state, this is again necessary and sufficient for its separability. Okay. So, this is what we are going to show. Okay. Good. Right. So, let us now, because we will have to deal with 2 mode state, Gaussian or not, that will come later. Okay. So, I am dealing with 2 mode states rho A B. A is one mode, B is one. So, you can think of A is within the lab of Alice and B is within the lab of Bob. Okay. So, because this is infinite dimensional system, writing it in matrix form and checking that condition will be non trivial thing. So, one can work in equivalent. So, this is basically one can work equivalently in Wigner distribution representation, okay, distribution function representation. So, in other words, we will have to cast this condition rho A B T B greater than or equal to 0 this condition has to be cast in terms of Wigner function. Okay. So, this is what we need to look at. Okay.
So, the last statement we wrote, so what we want to show is, we know this rho A B partial transposition of B should be greater than or equal to 0 if the state is separable.
No, what I am going to show for the two mode state case, if the state is known to be Gaussian, then this condition is necessary as well as sufficient. That this condition is necessary anyway is true, because Peiress's criteria, necessary criteria. For two mode Gaussian state, we will show that this is also sufficient for separability. Okay.
So, we want to show what will be the equivalent conditions on the Wigner function represented.
Exactly, exactly. What will be this equivalent condition in terms of Wigner distribution function, and then we will restrict ourselves to Gaussian states, two mode Gaussian states. Okay. So, if I take this, you can look at just single mode case, and then we will go to, because we are dealing with two mode case, we can directly go to the two mode case also. So, the Wigner function W rho x and p. So, these are the dimensionless quadrature variables. So, this is the kind of notation that we have used. It is minus infinity to plus infinity d of x prime x minus x prime rho. So, this rho is single mode case, okay? X plus x prime, then exponential of iota x prime p. Okay. So, this is the definition of Wigner function. Say some people say 1 by pi, and then here you can have twice here and then this x prime by 2, but that is okay. I mean, this is so we can take this. So, the notation that we have used in the sense that the Wigner function is basically what was that, the trace of rho and then t of alpha and 0, where this alpha is x plus I p by root 2. Okay. So, this is what we have defined. So, in that way this is the form, right. Okay. So, now let us take the, and these are all, so these are the position eigenstates. Okay. So, that means these are eigenstates of the observable x hat, right. So, now let us take the Wigner distribution of rho transpose. I will use the same definition. So, rho transpose x p is equal to minus infinity to plus infinity. This is d x prime x minus x prime rho transpose x plus x prime exponential of I x prime p, right. That is the definition. Okay. I mean, this is for density matrix, this is for any operator, same definition. So, now because this is transpose, I can interchange these two. So, this will be minus infinity to plus infinity dx prime, this is x plus x prime rho x minus x prime exponential of I x prime p, right. Okay. Now, our original definition is here minus x prime. So, let us take x prime is equal to minus x double prime, this is my definition. So, then this will become minus infinity to plus infinity d of x double prime x minus x double prime rho x plus x double prime, and now exponential of I x double prime then minus p. Okay. Is that correct? Because you have changed x prime to minus x double prime. Which one? Yes, minus sign, but you know there is also change in integral. This will be plus infinity, this is minus infinity. So, ultimately nothing will change. Okay. And this is what? This is nothing but Wigner distribution of rho at x and minus p, right. Okay. So, you see that for a single mode case, the Wigner distribution of rho transpose is same as Wigner distribution of rho, but you have a mirror reflection. Okay. So, if I look at this is x and p. So, I take this point which is x and p. Now, you go to this point, right. So, like this is my mirror. So, this is x and minus p, right. This is the mirror reflected state. Okay. Now, is this a symplectic transformation x p to x minus p? This is not, okay, because you know it will not satisfy this relation. So, if I take this transformation x p to x minus p, which is basically your 0 0 minus 1 acting on x p, right. So, this is does not belong to S p 2 r, right. This is not a symplectic transformation. This is mirror reflection. Okay. So, therefore, you cannot think of as a for every such S belonging to S p 2 r, one can figure out a unitary transformation, right. So, that this rho will go to U s rho U s dagger, but for this mirror reflection we do not have that. Okay. Right. So, anyway, so this is what we have seen. So, same thing can be done for the two mode case. So, let us say rho a b, this is a two mode state. I am not saying whether Gaussian or not, A and B are the two modes. So, then the Wigner distribution of rho a b, here it should be x 1 p 1 x 2 p 2. So, I remember I use this notation. So, I have also changed it later, but that is okay. So, this is my notation, this is x 1 hat p 1 hat x 2 hat p 2 hat. This is the notation I will be using here, and similarly this r vector is x 1 p 1 x 2 p 2. Okay. So, instead of this you can just write as r transpose. Okay. So, this is here it will be minus infinity to plus infinity d of x 1 prime d of x 2 prime x 1 minus x 1 prime x 2 minus x 2 prime rho a b, then x 1 plus x 1 prime x 2 plus x 2 prime multiplied by exponential of iota, this is x 1 prime p 1 plus x 2 prime p 2, right. This is the the two mode Wigner function, just like here. Okay. So, now if I apply, what I am applying is, so what I want to get is rho a b t b r. R transpose, yeah, because R is column vector, this is row vector. So, I want to get the Wigner distribution function of this thing. So, as you can see, what will happen here, I will have to replace this row by row partial transposition, and again then yeah. So, basically this is I will just you know this dx 1 prime, dx 2 prime, I mean maybe I do not do that, this is, you can figure out. So, this should be equal to rho a b, then this is x 1 p 1 x 2 minus p 2. Just reflection, this is partial mirror reflection, or you can say, because p going to minus p is time reversal transformation. So, this is, you can say this is partial time reversal, okay. Because you can do entire time reversal, that is physical, but this is not, this is partial time reversal, okay. And this I can write it as a b, this is, let me call it as lambda r, then its transpose. And what is lambda? Lambda is this matrix diagonal of 1 1 1 minus 1, right. That is how we get it. Okay. So, you see that under partial transposition, the Wigner function, it gets transformed like this. Okay. Now, the question is that if rho a b is separable, then this is also a valid state, right, under partial transposition, and therefore, its Wigner function must, does make sense, right. So, therefore, this is a bona fide Wigner distribution function if rho a b is separable. Do you agree with me? Right, because this has to be a valid Wigner distribution function if rho a b is separable. Okay. Now, how do I figure out that that this is a valid Wigner function? I mean, if it is separable, of course, it has to be, but otherwise how will I figure it out? Okay. So, let me erase this part. So, we know that rho a b is a 2 mode state. I mean 2 mode, 1 mode, it does not matter, or multi mode. So, this means that we will have to satisfy these stronger form of Robertson-Heisenberg uncertainty relation, right, which tells me that gamma plus iota by 2 omega greater than or equal to 0, where gamma is the covariance matrix. So, gamma j k is equal to this thing delta r j delta r k with respect to rho, right, and what is delta r j? Delta r j is r j minus R 0. Okay. So, this is my covariance matrix, and of course, omega is this one iota sigma y 0 0 iota sigma y, right. This is my this omega. So, for any state, not necessarily 2 mode, any state, this has to be satisfied, right. This we have seen. In particular, gamma has to be positive definite, right. Now, when you apply this partial transposition, okay, so what will happen to gamma? So, so partial transposition means that what is the partial transposition? So, it tells me that this R vector, actually this one also, this will go to lambda R, okay, where lambda is this diagonal 1 1 1 minus 1, right. Okay. So, therefore, you can figure out what will happen to this gamma under partial transposition. So, under partial transposition, what will happen is that gamma, it goes to lambda gamma lambda. Basically, if you look at these, only places where you will have change, where one of them is the P 2, right, the last quadrature, then you will have a basically negative sign, right. Other than that, nothing will change. If both of them are P 2, then also nothing will change, because both of them will go to minus, right. So, this is exactly what you will get to see. So, this you can verify, it is not difficult, you can verify. So, basically this is your transformation as well as this. Under this partial transposition, this is under P T. Okay. So, let me call this as gamma tilde. Now, if rho a b is separable, then gamma is gamma tilde, because what is it that I have done? I have basically changed this covariance matrix, right. So, gamma tilde is also a bona fide covariance matrix, right. Do you agree with this? Because whatever I have done is for a separable state, this is, so basically what my point is that if I take rho a b t b and then I calculate its gamma, okay, rho a b is a separable state, I take its partial transposition and then I calculate this gamma, this should be equal to this gamma tilde, which is lambda gamma lambda. Is that clear? Okay. So, this is also a bona fide covariance matrix. What does it mean? It means that gamma tilde plus iota by 2 omega greater than equal to 0. So, for a separable state, you should have this as well as this. This is true for any state, but this has to be done, this has to be true for a 2 mode separable state. Is that clear? Okay. Now, I can cast this in another form. So, this is equal to lambda gamma lambda plus iota by 2 omega greater than equal to 0, right, this condition. So, now let us take lambda outside gamma plus iota by 2, because lambda is a diagonal matrix. If I multiply it by itself, then it will remain same. Can I write that? Because lambda square is identity. So, therefore, nothing has been changed, right, and see that this is a similarity transformation, because I am basically multiplying by this diagonal matrix. Okay. So, this is a similarity transformation real. So, therefore, this tells you that gamma plus iota by 2 lambda omega lambda must be greater than equal to 0. So, this condition is equivalent to this one also, because this is a similarity transformation. Okay. So, I can just get rid of that. And in fact, you can think of it as a unitary transformation, because this is a 1 1 1 minus 1. So, under unitary transformation nothing will change, positivity will not change. Okay. So, therefore, so for a 2 mode separable state, this has to be satisfied as well as this has to be satisfied. Okay. Is this clear? Okay, good. So, let us see now what is it that we want? We want a separability criteria of 2 mode state in terms of this gamma matrix, because that is what we want. Okay. Now, of course, as we know that if the state is non-Gaussian, then everything is not captured by this gamma matrix, that is of course true, but let us see how far we can go. So, what exactly we want is criteria in terms of elements of this gamma matrix for the separability of 2 mode state. Okay. So, this is what we want. Okay. So, you remember that this is your uncertainty relation, right. Now, uncertainty relation. So, basically this is what? This tells you that your state has to be positive semi definite, right. I mean, in one form or other, this is the criteria. Okay. So, let us see that so this is so generally we talk about the product uncertainty like this Robertson, Heisenberg, etc. So, let us go into some uncertainty, but this is equivalent. So, what I look for now is take this so let us choose 2 real vectors d and d prime. These are, so let us say d is equal to d1, d2, d3, d4 and d prime is equal to d1 prime, d2 prime, d3 prime, d4 prime. These are all real vectors R4, any 2 real vectors you can choose. Okay. So, let us now define this observable d, which is d1 x1 hat plus d2 p1 hat plus d3 x 2 hat plus d 4 p 2 hat. So, this you can write as basically d and then these are vector like, right, this is what you can write. So, this is, you understand that this is a Hermitian operator because this is real. Similarly, you can take x d prime also, right, which is your d prime and then r vector, right. Okay. So, now let us look at this thing. So, delta of x d. So, what is that? This is basically your x d minus average of x d with respect to rho. Okay. Right. So, this you can write it as therefore, d 1 of delta x 1 plus d 2 delta p 1 plus d 3 delta x 2 plus d 4 delta p 2. So, which basically you can write it as d transpose delta r this, right. Similarly, you can have delta of x d prime. So, now what you do is you take this sum uncertainty, okay. These are any two observables. In fact, if I take the commutator of x d and x d prime, what will be that? It will be d 1 d 2 prime x 1 p 1, right. Okay. And right. Okay. And then what else? Plus am I writing it correctly? Let me see, d 3 d 4 prime minus d 4 d 3 prime into x 2 p 2. Is that correct? If I take the commutator, is not it? This is your x and this is your x d, this is x d prime. So, this has to be the case. So, therefore, this is, because this is iota, this is also iota. So, iota d 1 d 2 prime minus d 1, I mean d 1 d 2 prime minus d 2 d 1 prime plus d 3 d 4 prime minus d 4 d 3 prime, right. This is exactly what you will have. Okay, good. So, let us look at this. Now, this we know that this is greater than or equal to 2 times delta x d times delta x d prime, right, with respect to rho, is not it? Okay, I mean you can put magnitude also, that does not matter. Okay. So, you can put a magnitude here. Now, this we know by this uncertainty relation is that this is greater than or equal to, because of these two,
It's delta x of d plus delta x of d prime, right? It's not x of, you're adding the variance of the second term,
which one?
the delta x of d rho, and then that's again a variance, right? This delta.
Sorry, yeah, sorry, yes. So therefore, this is, because of these two, I can say that this is less than equal to expectation value of x of d prime with respect to rho. Is that clear? Because this is the standard uncertainty, right? Okay. And this is according to our calculation. This is basic, because this is constant. Okay. So, whatever rho you take. So, this is d1 d2 prime minus d2 d1 prime plus d3 d4 prime minus d4 d3 prime, magnitude of that, right. Okay. So, basically, this uncertainty relation is equivalent to this uncertainty relation, because anyway we are dealing with the uncertainties. Okay. So, I mean, and this has to be true for all d and d prime belonging to R4, whatever be your d and d prime. In fact, what you can figure out from here is that this expression yeah, I mean basically this one, delta of x d square rho. If I calculate that, this you will see that this is nothing but something like this. Okay. D transpose gamma d. Okay. And in fact, more than that, this is d transpose gamma plus iota by 2 omega d. Why? Because this d transpose omega d, this is 0. If you calculate d, this is what you will get. Okay. So, therefore, this is your, basically this is the form, and similarly here. So, you see that positivity of this, right, will tell you that this quantity is of course greater than or equal to 0, right. Similarly, this quantity. So, where you replace d by d prime. Okay. So, effectively, if you look at this uncertainty, you can also cast it in this form for arbitrary d and d prime. And if you look at this quantity, this thing, it will turn out like d prime transpose omega d. I mean, if you look at the form of omega, omega is your, what is the form of omega? I sigma y 0 0 I sigma y. So, if you take that form, this is what you will get. Okay. Right. So, therefore, the uncertainty relation that we are looking at, so this uncertainty relation, you can say that this is equivalent to which is what I have written there. Okay. For all D and D prime belonging to R 4, right. Is that clear? Okay, good. Now, let us come back to this, which is the case if rho A B is separable. This has to be satisfied, right. So, what will be the change in this? This is also an uncertainty relation, right. So, what will be the change in this relation? Because you see I have not changed gamma. So, therefore, this part should not change, nothing has happened here. So, this condition will be equivalent to and what is this? This is what I am calling as omega tilde, right. So, you see that for a 2 mode separable state, this has to be satisfied, this also has to be satisfied, and this comes from here because nothing has been, because gamma has not been changed. This is why I cast this relation in this form, while gamma remains same, only change in this omega, where I call this omega tilde as lambda omega lambda, right. So, for a 2 mode separable state, both these conditions need to be satisfied. Is it clear? Right. Okay. So, let me erase this part. Yeah.
Omega and omega tilde are just related by a simple unitary transformation.
Yeah, this is just yes. So, lambda is the diagonal 1 1 1 minus 1.
So, which means if one of those conditions is satisfied, so since omega and omega tilde are related by a simple unitary transformation, it would also imply that the second one is
no. This is not satisfied for arbitrary rho. This has to be satisfied if rho is separable.
Oh, okay.
Okay. So, if rho is a 2 mode state, this is anyway satisfied. But if on the top of that, if it is separable, then this is also satisfied. And again, this is for all D and D prime belonging to R3 positive.
So, for a given rho, if the second condition is not satisfied, then that
means that the state is entangled.
Entangled, okay.
Because for given rho, this is anyway satisfied. Okay, so maybe I'll just write here d prime transpose omega d is equal to magnitude of d1 d2 prime minus d2 d1 prime plus this is d3 d4 prime minus d4 d3 prime. Okay. And now, if you do this thing d1 transpose omega tilde d, you remember omega is lambda is, so okay. So, omega tilde is lambda omega lambda, which is basically diagonal 1 1 1 minus 1, then omega, then diagonal 1 1 1 minus 1. Okay. Right. I mean nothing, I mean basically this will be your I sigma y 0 0 minus I sigma y. In omega this is both are plus. So, for omega tilde this is minus. Okay. So, what you will get to see here is that the same thing d 1 d 2 prime. So, this I am not calculating, you can do that, this is simple, d 1 d 2 d 2 prime minus this is d 3 d 4 prime minus d 4 d 3 prime. Okay. So, just this is the change. Okay. So, you see that for a 2 mode separable state, therefore, for any 2 mode separable state, what we have is this thing, that x delta x d square rho plus delta x d prime square rho is greater than equal to. So, this part tells you that this is greater than equal to magnitude of this. This part tells you that this is same thing greater than equal to magnitude of this. So, I can say that this is greater than equal to d 1 d 2 prime minus d 2 d 1 prime plus magnitude of d 3 d 4 prime minus d 4 d 3 prime. Can I do that? Because you see this is this form and this is just a minus sign here. So, both of these has to be satisfied for a 2 mode separable state. For a 2 mode separable state, this is the condition that has to be satisfied for all d and d prime belonging to R 4. Is that clear? Because of this, that here is just a plus sign, here is minus sign. So, this has to be satisfied. Okay. Okay, good. Okay. So, okay, so this is fine. This is for any 2 mode separable state that has to be, this has to be satisfied. So, let us go back to here. If I take this thing, that x d and x d prime, if this is 0, that means they commute. What does it mean? It means that this is transpose omega d is 0, right? Because you see this is how we obtain here. So, this is what, so basically if you calculate this, I think it will be of this form minus I d prime tilde omega, something like this it will happen. Okay. So, this is 0 means this is also 0, okay, right. Of course, so what does it mean? It means that it does not mean that this is equal to 0. So, this is greater than equal to 0, that is what it says if they are commuting. Okay. It does not mean that this is equal to 0. So, in other words, if they commute, it does not mean that I can make these two terms as small as we can. Right? This is the standard uncertainty that we understand. So, commutation of these does not mean that we can make these two as small as we can, right. Okay. Right. Okay. Now, you see that if these two commutes, then this is 0, therefore, this is 0. What can I say about here? Can I say that this is also 0 if they commute? Not necessary, right. Look at here, this is 0. This does not mean that this is also 0, because in order that this is also 0, you will have to have individually this is 0 and this is 0, right. Okay. So, for a separable state also, even if this is they commute, okay, I understand that this has to be satisfied, but it does not mean that for a separable state this is also 0. In order that this is also 0, of course, you will have to have d prime transpose omega tilde d is also 0, which means that this is 0 as well as this is 0. Okay. So, in general, commutation does not mean that even for separable state this part is 0. Okay. Right.
And those conditions are for all d and d prime, right?
Yes, yes, yes.
It is 0 for some special d's.
Exactly, exactly. Yes, yes. Okay. So, now let us see that this is of course in terms of these real vectors. So, still it is not very useful. Okay. So, let us see whether we can cast it in a form where it will become more useful. Okay. Right. Okay, then. So, let me, what shall I do? Let me erase this part. Okay. Okay. So, now if this is a separable state, okay, I mean not necessarily separable. So, if this is separable, rho a b is separable, then we know that, so this will imply that if I apply some unitary on A mode and some unitary V on V mode, rho a b u a v b, this dagger, this is, so this is also separable. In fact, if you replace it by entangle, this is also entangled, right, because under, so these are all these are unitaries. So, under local unitary transformation, separability or entanglement does not change, okay, it will not change, right. So, let us see that as I said that this transformation, partial transposition which takes r to lambda r, where lambda. So, this is not a symplectic transformation, this is not symplectic. Right. But what we want is, if I apply some symplectic transformation, namely if I take, let us say, if I apply this S, which is S p, because in this case this is 4 R, right, this is the symplectic group. So, if I apply this S, and we have discussed earlier that this can correspond to some unitary S, which is generated by quadratic Hamiltonian, right. This we discussed in at length, right, although we have not mentioned how to get this exactly, but we have given prescription, right. So, this is my unitary. So, under symplectic transformation, so R going to S R, which is my R prime, right. So, rho will go to U S rho U S dash, but this is not a, not local unitary, right, in general, right, because I cannot guarantee that this can be written in this form, I cannot guarantee that. And this is important because we are dealing with, we want to figure out separability criteria. So, I cannot apply a global unitary which can make a separable state into entangled and some entangled state into separable. So, I am not supposed to apply such global unitary here, right, which can change the nature of entanglement. So, what we can do is we can restrict ourselves. So, you restrict to the subgroup which is S p 2 R tensor product S p 2 R. So, this is like, because I will have to apply the symplectic transformation. So, which is like local symplectic transformation, okay, right. So, this is a subgroup of S p 4 R. So, S p 4 R, we said that this is, so S p 2 n R is n into 2 n plus 1 parameter group. So, in this case this will be 10 parameter, right, because this is n is equal to 2. So, 2 into 5, so 10 parameter, whereas this is 3 parameter, right. So, this is 3, this is 3. So, this is basically 6 parameter total. Okay. So, you will have to restrict into this kind of symplectic transformation, because that will only guarantee. So, basically what you need to look at is S, which is of this form S 1 0 0 S 2, where this S 1 and S 2, these are from S p 2 R. Okay. So, that the corresponding unitary U of S, it should be like U of S 1 0 0 U of S 2, or you can say, do not write like this, you can say this is U of S is equal to U of S 1 tensor product U of S 2, right. This is what you will have. So, local unitary transformation corresponding to local symplectic transformation. Okay. So, this is what you need to look at. Okay. So, let me erase this part. So, what we want is, under such local symplectic transformation, how to get a simpler form or a canonical form of this criteria. This is what we want, okay, so that we can use it further. Yes.
Between D vector and the row.
Nothing, no relation.
No relation.
No, no relation. This has to be true for arbitrary D and D prime real vectors, and this is what is equivalent to this uncertainty relation. I mean both the uncertainties for separable states, okay. Because this has to hold good for arbitrary D and D prime. You can prove that this is equivalent to this condition, that gamma plus iota by 2 omega greater than equal to 0, this is for any state, and for separable also this is true, iota by 2 omega tilde greater than equal to 0. So, both of these should be satisfied. Yes, yes, that is true, but you know, as I said, this condition and this condition are equivalent. Okay. So, we want to use this condition instead of this one, because this may not be so useful. We want to use this after looking at their canonical form under this local symplectic transformation. Okay. So, that means I apply local symplectic transformation on the state, 2 mode state, and then figure out what will be a simpler form than this regarding uncertainty. Okay. So, this is what we are looking for. So, you may see that why to make our life difficult to introduce these arbitrary real vectors here, but as I said these two are equivalent, okay. And this will be more useful what I am going to do now rather than this one. Okay. So, some relation between what?
Row, or like for example, if you measure something on row, then it should be some eigenvalue.
Yeah. So, this is so all the information about rho is on the left hand side. On the right hand side there is no information about rho. This is what the typical state independence uncertainty relation tells you, right. The right hand side should be independent of rho.
X is connected with R, right? Then in that gamma.
So, if you write down this for every choice of D and D prime, okay, you will get a list of conditions. Those list of conditions are equivalent to these list of conditions, which will be independent of D and D prime. Essentially what is it that we are looking for? So, you take for example, this eta, which is we can say like this. So, which is an operator. So, let us say this is alpha 1 x 1 plus alpha 2 p 1 plus alpha 3 x 2 plus alpha 4 p 2, where these alpha j's are complex number, let us say, right. And now, you take this eta dagger eta, right. This has to be a positive operator, no doubt of it, eta dagger eta, right. Okay. And this means that if I take trace of eta dagger eta with respect to rho, this has to be positive for all states rho, right, is not it? This has to be the case, because this is positive, right. So, this condition involving complex numbers is equivalent to this condition involving these real vectors, okay. Same thing. So, I mean this condition is also equivalent to this. So, whatever way you want, you can do that. Okay, maybe I will just erase this part. So, let us take this S belonging to sp2r. As I said, I will consider now only this local symplectic transformation, and so I can write it as S1 0 0 S2, where this S1 and S2 are symplectic transformation from sp2r, right. I can always write it because this is in this form. Okay. Right. So, under symplectic transformation, so let us say I take this gamma. So, I am dealing with two mode state. So, I can always write it as A C C transpose B. I can always do that, right. This is a 2 by 2 matrix, this is 2 by 2, this is 2 by 2, all these are real 2 by 2 matrices. And because gamma satisfies this thing, gamma plus iota by 2 omega greater than equal to 0, right. You can show that from here that A as a matrix has to be greater than equal to 1 by 4, because this is your in uncertainty relation. B has to be also 1 by 4. I mean, there will be further conditions that I am not writing. So, this is, so A basically transpose is equal to A, B transpose is equal to B, but C is a real matrix. Okay. All these are real matrices. Okay. Right. So, this I can always write any covariance matrix. So, let us look at, so we know that under symplectic transformation gamma goes to gamma prime, which is S gamma S transpose, right. Under symplectic transformation, this is what has happened. So, this is S1 0 0 S2, this is A C C transpose B, and then this is S1 transpose 0 0 S2 transpose, right. This is what it happens. So, if you now do it, so this is S1A, then S1C, then S2C transpose, then S2B, and then S1 transpose 0 0 S2 transpose. So, this is S1A S1 transpose, then S1C S2 transpose, this has to be S2C transpose S1. So, this is S1C S2 transpose of it, then this is S2B S2 transpose, right. Okay. So, you see that under this local symplectic transformation, so under local symplectic so this I can call it as S local, okay, because this is a local symplectic transformation. Local symplectic transformation, you know, this A goes to S1A S1 transpose, right. So, this is like, because this is a single mode covariance matrix, right. For this A, this is a single mode covariance matrix. B goes to S2B S2 transpose, again a single mode covariance matrix, and C goes to S1C S2 transpose, right. Is this clear? Okay. So, if so because this is a covariance matrix of a bona fide 2 mode state, this is also covariance matrix of a bona fide 2 mode state, because this is, you know, the way it transforms, right. Okay. So, now let us see therefore, what are the invariants of these covariance matrix under such local symplectic transformation. So, you see that determinant of A, it goes to so this is under local symplectic transformation, So, this goes to LST. So, this goes to determinant of S1 A S1 transpose, right, and this you know by the rule of determinant is that now determinant of any element. So, this S1 and S2 are elements of SP2R, and this is area preserving transformation. So, determinant of S1 is equal to determinant of S2 is equal to 1, all of them are 1, and you can think of it like you know SL2R, I mean you know invertible determinant 1 transformation in 2 dimension, okay, real transformation. So, therefore, this will be equal to determinant of A, because determinant of S1 is 1, determinant of S1 transpose again 1. So, this is determinant of A. Let me call this as I1. So, therefore, this determinant of A is a symplectic local symplectic invariant of this gamma, right. Determinant of B similarly under local symplectic transformation, it goes to determinant of S2B S2 transpose, which is equal to determinant of B. Let me call it as I2. So, this is again a local symplectic invariant. What about determinant of C? It goes to determinant of S1 C S2 transpose. Again this is determinant of C, because determinant of S1 is 1, determinant of S2 transpose is 1. So, therefore, this is determinant of C, I call it as I3. So, you see that this gamma which I have taken in this form, it has these local symplectic invariants I1 which is determinant of A, I2 which is determinant of B, I3 which is determinant of C. These are all local symplectic invariants, they do not change under the local symplectic transformation. Okay. But if I look at the determinant of gamma itself, so this goes to determinant of S gamma S transpose, right. Now, S is a symplectic transformation, again determinant of S is 1. So, therefore, this is also determinant of gamma. So, this is again a invariant, symplectic invariant. I mean this is symplectic invariant under any symplectic transformation, not just local symplectic, okay, right. So, this is so therefore, under local symplectic also this is invariant, right, but one can express it in a different way. I think now this is a typical form. You can also figure out some other invariant with respect to which you can write the invariant this determinant of gamma. So, let us look at trace of A. Now, this J is iota sigma y, you know this appears in omega, right. So, A J, C J, B J, C transpose J. Okay. I mean this is a quite convoluted form, but yeah, it is not difficult to see. So, now you know the in the case of, so if S1 and S2 these are of SP2R, this is what I have chosen. So, S1 J S1 transpose is equal to J is equal to S2 J S2 transpose. Okay. So, this is how the symplectic transformations will behave, right. So, this will transform to trace of, now A I have seen it will go to S1 A S1 transpose, right. This is your A. J will remain same as J because that is a symplectic invariant under this transformation. C will go to S1 C S2 transpose, J will remain invariant. Then B will go to S2 B S2 transpose, then J will remain invariant. Then C transpose will go to S1 C S2 transpose of it, and then J will remain invariant, right. Is that clear? This is how it works. So, therefore, this is under local symplectic transformation. So, trace of, now this is S1 A. Now, let me club this one, S1 transpose J S1. In fact, if S1 is an element of this sp2R, you can also show that S1 transpose S2 transpose are also elements of sp2R. Okay. So, that is not an issue. So, this is S1 transpose J S1, then C, then S2 transpose J S2, then B, then this will be S2 transpose J. Now, here it is S2, then again no sorry, yeah, right, S2 transpose J. Okay. So, then it is C transpose, then it is S1 transpose J, right. Now, because of trace I can take this, because of the circularity of trace, so I can take this here. So, this will be basically your, because I said that these are also symplectic transformations. So, this is A J C J B J C transpose J. So, you see that under local symplectic transformation, this quantity is also invariant under S local, and this we call as I4. So, you have 4 invariants here under local symplectic transformation, I1, I2, I3 and I4, and in principle one can write down determinant of gamma in terms of this I1, I2, I3, I4. So, therefore, this is not an independent invariant, one can express it in terms of those invariants. Okay. Right. Okay, good. So, what is the utility of using these invariants? Why should I bother about that? Okay. Why should I at all care about this invariance? Okay. So, that is basically the question. Good that we have considered the invariance and all that, but now the idea is to cast this uncertainty relation in terms of these invariants, local symplectic invariance, and that will do the job, you know. So, once we do that, then things are fine. So, what I will, maybe I do not have the time now. So, what I will just write here is the uncertainty relation involving this local symplectic invariance, okay, and then I will prove it next time. So, you understand that why we need to consider only local symplectic transformation, because otherwise it will change the character of entanglement or separability. Okay. So, that is the reason. So, let me just write down for you the the uncertainty relation. So, this Robertson-Heisenberg uncertainty relation in SP 2 R cross SP 2 R invariance form. So, this is for any state, any two mode state. So, determinant of A, which I said that this is one invariant, local symplectic invariant, times determinant of B, this is another local symplectic invariant, plus 1 by 4 minus determinant of C, this is again a local symplectic invariant, minus trace of A j, C j, B j, C transpose j greater than or equal to half or 1 by 4 determinant of A plus determinant of B. This is for any two mode state, two mode covariance matrix, gamma is equal to A C C transpose B. Okay. If gamma corresponds to the covariance matrix of a separable state, then additionally we have basically this one, determinant of A, determinant of B, or you can okay. So, plus 1 by 4, now here it is basically plus okay, determinant of C square minus trace of this is A j, C j, B j, C transpose j greater than or equal to 1 by 4 determinant of A plus determinant of B. So, basically if I combine these two, the condition that we will have is minus magnitude of this. Okay. If I combine these two, right. So, if we have a two mode covariance matrix of a two mode separable state, then this is what the condition you will have to satisfy for any two mode separable state. Okay. So, this is you can say that the necessary condition and this is SP 2 R cross SP 2 R invariant form. This is the necessary condition for separability. Okay. So, for any two mode separable state, the corresponding covariance matrix which is of this form, it has to satisfy this condition. Okay. So, this is what I will prove next class, proof of this. And once it is done, then proving it for the opposite way, that means for Gaussian state this is also sufficient, it is very easy, because for separable Gaussian state this determinant of C is always greater than or equal to 0. So, therefore, that will make life easier. Okay, good. So, let me stop here.